Let's see, if I take that one and move it there, move that one there, and I take these two and move them like that. Nah, that's not right.
Ow! I'm studying! I promise!
So it seems kind of pointless to make a video about how to combine a bunch of forces on one object and to make a video about it. So it's kind of stupid. Except for the obvious way of doing this actually ends up breaking when you have a lot of different objects in one system. So to fix that, you kind of have to look at a different way of doing things. So this video is going to cover the obvious way of doing things, why it breaks, and then a different method that I've used in the past for a couple different projects that works pretty well and it doesn't have a problem with hundreds of different objects all in one thing. So while you're looking at the example up to the side, this video is only going to cover how to work with the forces, and there'll be some references to colliders and overlap corrections. Well, that won't be in this video, but I'll be making more videos about that later because it's a little bit too complicated to include in this one. So using the basic, obvious way of doing this, you have an object, you look at all the collisions that are attached to that object, and you apply whatever forces like gravity, friction, some kind of wind, whatever. And then you add all those together, move that object, and then move to the next object. The problem is that only works when you have one or two objects interacting with each other. As soon as you have more than one collision, things start getting really weird, and I'm going to go over those reasons and results in just a second. So to explain why that doesn't really work, let's take a look at this particular example of three balls rolling in the same direction at the same velocity. Well, in reality, those aren't going to touch each other, they're just rolling together, there's a little bit of gap between them, no big deal. If you start moving one object at a time, like these three options, randomly pick one of these, only one of the three gives you the right result, because if the very front ball moves like a number 3, for example, then it leaves room for the next ball, and then that one moves, it leaves room for the next ball. But if you have options like 1 and 2, and you move ones in the middle, it starts overlapping another object, which creates a collision, and now there's a collision that should never existed in the first place. When we move to the next example, you have an object in the middle, and it's going to go upward, and then the two outside balls are going to move inward and collide with that particular object. So which one do you pick? So if you look at these different options, the little green line has all the resulting vectors after all the collisions and movement has occurred. So which one is right? The answer is 9 of them, because it should look like this, which is the ball moves upward while the other ones move in, which leaves a little bit of room for the collision start. The collisions happen at the same time, and the ball is ejected even faster upward. So if you go back to the original 3 options off to the side, and you see that all the little vectors are going the wrong direction, it becomes very difficult to predict which is the right answer, and all of them in this case are wrong. So to stay with this particular obvious method of picking one, moving to the next, moving to the next, the solution is simple. You just pick the proper order, and then everything works out in the end, and you don't have to go back and forth. It's efficient. The problem is that how do you pick the right one on every single frame? You don't know where all the collisions are going to be without looking at everything first, and it's having some fancy formula to figure out what the right order is. Otherwise, you end up with that, where everything gets really weird really quick. So picking the right order, picking the right options is just very unlikely. So to compensate for the fact that we can't work with one object at a time and complete everything that just doesn't work, you kind of have to look somewhere else to figure out what a better option is. So a real option would be to look around us and see how things work in the real world. It works for AI, it works for physics, it works for a lot of different complex systems. We can kind of look around and see how things work in the real world and kind of emulate that. So how does the real world work when it comes to physics? Everything is continuous, and everything happens in this particular way that they all interact at the same time. We can't do that in code, but what we can do is find a way to have all the collisions happen along with all of the movements from gravity and wind and friction, and then everything moves together just like in the real world. So how is that going to work? I'm going to give you the algorithm in just a second, and it ends up being a lot of different for loops, so it ends up going through the same things multiple times. You have the benefit of being able to work through things in a random order instead of having to just know the right order every single time. So using that real world model, we can make a quick algorithm as long as we compensate for a few things. So we have to have all the collisions happening, which needs to probably be first. We need to have all the forces acting on it after those collisions are added together, because we don't want to have forces like gravity and wind changing how the collisions happen from the previous frame. So we have collisions, then we have all the forces added, and then things have to move. Because everything has to move all at the same time, we have to actually have everything start to overlap because things are really trying to work with each other properly. So you might have one ball partially inside of another ball. I've actually seen instances where an object will teleport through a wall because it was moving so fast. So those type of complications like colliders and overlap correction will be in other videos because, well, they're complicated and a lot of little nuancey things that have to be compensated for, which are beyond this video. But they'll be included into this particular algorithm that will be used through those videos as well. So as a preface to this particular algorithm, something has to change with any kind of structure that you have for storing an object. You're going to need a list or expandable array of some type in order to compensate for a bunch of forces being added to an object before the object moves itself. There's going to be a delay between all the forces being added before a move actually occurs. So you need a kind of a list for all that. There's also going to have to be a list or an array of some type in order to have a list of all the different overlaps that have to be corrected. Again, this will be another video, but it needs to exist in your structure now because you don't want to change that later. So with those in mind, once you get into this algorithm, it becomes a little complicated, and there's a lot of for loops, but it actually is pretty simple overall. So first you take all of the particular for loops for each item you have, and then you look through all the collisions that are possible with that object, preferably just the ones that are close by that have a chance of being in a collision, just to save some processing speed. Then you look at those, you have a force that's applied to your object, and then you add that to that list of all the known forces of an object. Once all objects have been processed, then you move out of that for loop into a new one where you look at each individual object in your list. You apply things like wind and gravity and friction on any other forces you might have, or any kind of interactions that you have from game environment, whatever. And then you take all those forces, combine them together with vector math, and you end up with an addition to the momentum that you already have, and you can do whatever you need in order to move the object. Once you've done with all of those, you go through the list yet again, after all the objects have been moved, and look for any kind of objects that are overlapping each other. So if you have one ball that's kind of overlapping into another ball, you have to decide how those two objects are going to move apart from each other so that they're not looking weird and being inside of each other. To do that, we'll go into another video. But you have to look at all the objects with all the different comparisons, because you might have one object with another object, and this object is also interacting with another one, so you might actually have to go downward with one of them. So all those particular movements are overlapping. You have to put them all into one big list, or all of them, and then move out of that for loop yet again, and then go through another for loop where you add up all the different vector movements from overlap, and then you apply that particular overlap movement to your actual position of the object itself. That should, over time, move objects away from each other enough so they're no longer overlapping in like 2 or 3 frames. Usually works out pretty quick, the user won't even notice. So what's the overall benefit of this excessive amount of for loops? Well, if you look at the original example I gave with this one, where the object's in the middle and 2 objects are going to try to collide with it, now we don't have to worry about ending up with these results. We just automatically end up with the right one. Because it's simple, we have overlap protection, we have some kind of collision, and everything's happening exactly at the same time, along with the moves happening exactly at the same time. but it gets a little more complicated, a little more steps along the way, but everything ends up working out for us in the long run. We don't have to predict a bunch of interactions in order to pick the right order to move things around anymore. So we end up saving a lot of time in the long run. Another benefit of this method, I think I mentioned it before, is that because each individual stage along the way is any order, doesn't matter which order it is, we can actually multi-thread the whole process. So you have one thread handling one section of the game board, another thread handling another section of the game board, or you randomly assign out of the list, this one goes to thread 1, this one goes to thread 2, and so on. And then you move out of that particular step, you move into the next one, you can multi-thread it all over again. You just need a schedule along the way. I'll be doing videos about that eventually. So hopefully that kind of explains why an obvious way of doing things might not actually be better. It actually might give you the wrong result in the long run. This kind of works that way for a lot of different programming projects outside of games as well. So sometimes it's better just to look at the real world, kind of see how things work out in that, and then try to simulate it even though it's not exactly obvious at the first go around. So I also mentioned I'll be doing videos on collisions, and those will be probably 2 or 3 videos. I'll also be probably doing one on overlap correction as well. It get a little complicated, so there's more than videos that have to come along for that. I also mentioned threads, which I'll be doing in the distant future because that's extremely complicated and requires quite a few videos to explain how they work.